In this video, I will explain how to do the residual stress simulation. This residual stress simulation uses the input of the thermal models, the temperature fields, and the phase transformations calculated in that model to calculate residual stresses, deformation. We want to use the same geometry and preferably also the same mesh. So the easiest thing to start is just to usually copy the model that we created in the thermal simulation. And let's call that mechanical. Okay. Then in our mesh, we want to change the element type of the whole geometry. We're not using heat transfer anymore, but we're going to use plane strain now. Reduced integration, quadratic elements. Okay. And next we're going to create the material for the mechanical simulation, so we can delete materials that we used in the thermal simulation and create a new material. Let's call it material 1, it's fine. It needs to have a user material now of user type mechanical. Also we need user dependent state variables, but we need 30 of those in the simulation. And finally here we need to have mechanical expansion, and we need to use the user subroutine uexpand for that. Okay, let's also delete these sections and create one new section of the whole material, that material 1 over there, and let's check our section assignment manager. Can delete these two and create a new one, so we assign this section to the entire pipeline. Yep. Okay. We need to replace the steps, because these are all heat transfer steps, with mechanical steps. So you basically can delete all those. Okay. And create all the new steps. Step 1, initial. And now this step needs to be static general over here. Okay. This one we can again do in one increment. We don't really have to adapt the time period now, because there's no time dependent behavior in the mechanical model, so you can all just have a time period of 1. Let's create step 2, which was heating 1, time period of 1 with it. Okay, let's do this again in 100 steps. Okay. Step 3, cool down. Sorry, insert 1, static general. Okay, in 1 step. The cool down. Cool down 1, let's see here, 1, -4, -2, let's increase this one. Okay. This this should be heating 2. And our final step should be cool down to 4, 2. Let's put that to a smaller number. Okay. Okay. Then for field output request, basically the most relevant properties to write out here are stress is the strain, total strain, plastic strain is handled internally. The displacement, discrete forces, contact, and the solution-dependent state variables. And let's write this out for evenly spaced time intervals. So let's do 10 time intervals. No, actually we should have done that for the initial step. So stress, strain, the other ones. Displacement, no forces, no contact, that's the V. Evenly spaced time intervals. For the initial time step, we only want 1. In the heating one, we want 10. Here, 1. Cool down 10. In heating is propagated is 10. In service 1. And this one we put to 10 already. Then we have the interactions, similar as in the thermal model. We want to deactivate the weld regions in the beginning. So let's call this weld speed 1. Model change. Let's select the weld 1. Okay, deactivating this step. And let's create similar one for weld P2. Okay, weld 2. Deactivating this step. Scan open the manager and make sure that this one, we need to edit it. Reactivate step 3. And well, B2 should be reactivated in step 6 in circle 2. So we are reactivating this step. Okay. For boundary conditions, we only need to suppress rigid body motion. So let's, in 2 points, fix one direction and 1 point fix the other one. So let's create fix y as initial displacement Okay. We can select, 2 points here next to each other on the weld. So we want to figure constraint at the new y direction. And then we want one of those 2 points constrained in the x direction. Let's choose this one. Done. New one. The next step is to tell Abacus to read in the results file of the thermal simulation and use that as predefined fields during this residual stress simulation. Can go ahead over here on the predefined fields, and we have to delete all these fields that we defined before. Okay, and let's start with reading in the temperature field. So let's call this temperature in the initial step, and we should read that into temperature there in the whole geometry. And we can choose here from results for output database file, and we can now here go ahead and choose the thermal.odb, or just type thermal.odb, and over here you don't really need the full plot. So initially we need to set here a first step and increment 1. Okay. Now because we have different steps, we had 7 different steps over here, we need to adapt this predefined field to in each step read in the correct temperature field. So we can do that over here, and in each step we want to basically modify. Okay, this one is correct. In step 1, increment 1 in step 1, and then in step 2 we want to modify it to step 2. And so the same thing in step 3. Until we have done all steps. Then we want to read in the phase fractions. However, there's a limitation in Abacus that it can only read in temperature, basically temperature data from an ODB file. So we need to do a little trick over here. I've provided a script called thermal postproc over here, and see how to run it. And basically what this does is it reads in the results from the thermal simulation and creates 5 new different result files. And in each results file, the temperature field has the, we put the phase fraction as a temperature field in that results file. So you can use the command on the top of the file, just change the output name like this. And now for each phase, it starts to read in the data and writes it out. This script has finished. Took a minute or so on my PC. So I skipped that part. But you can see now in our folder, we've created actually 10 new files. So for each phase, we have created a new output file. So the thermal output file, where the temperature field contains actually the austenite phase fraction, and we have contained a .prt file. So every ODB file needs a PRT file. And we can read those in Abacus. So let's open Abacus again and create a new predefined field. In the initial step, let's call this fraction of ferrite. And this needs to be a field over here. Okay, the whole geometry. Okay, and it's to be from results or output file. Field variable number 1 is ferrite. Now we need to select here the thermal ferrite output file. And as output variable we need NT, stands for nodal temperature, and step 1, increment 1. Okay. Then again we need to adapt this in every step. Step 1 is probably okay. Step 2 to step 2, etc. And finally step 7. Okay, I want to do this for all phase fractions, but the easiest, quickest way to probably do that is to just copy this ferrite phase fraction now. And let's call it ferrite fraction perlite in the initial step. Okay, and then in our initial step where it is created, choose here now the perlite file. And all the other steps should then still be correct. So if I choose step 5, it should still say beginning step 5 over here. Okay, so let's do that for all our phase fractions. The next one is bainite. Need to make sure to adapt this in the initial step. Martensite. Let's close this. And finally, austenite. Another thing we should do, and I forgot in the other fields, is to change the field variable number. So austenite should be field variable number 5. So that was the case in our thermal simulation. In our thermal simulation, as you can see, top of the file, these are the field variables, and also in our mechanical simulation, should have in these predefined fields. So basically say numbering for phase fractions. So austenite should be 5. Bainite should be 3. The fraction ferrite was 1, that was correct. Martensite is 4. And finally perlite should be 2. Okay, now all the fields should be read in correctly. We can now create a job. Mechanical, let's give it the same name. Okay, and write the input file. Okay. So we now should have the input file over here. Again, we would like to have readable outputs. So we need to give names to these state-dependent variables provided. Again, an input script. So we have mechanical input.py over here. You can run it, change the file name. And this should again create a new file, which should now be called mechanical mesh.input, which has the correct state-dependent variable names inserted. Similar as to the thermal simulation, we also need to specify some additional input parameters. So the file for the mechanical simulation has to be called set parameters mechanical.f90, and here you need to set all the hardening exponent of the power law hardening that is implemented in the model. You can set an annealing temperature. So basically, if the temperature reaches above this temperature, this resets the accumulated plastic strain over there, which usually this temperature should be close to the melting temperature. And we should again give in a props file. The correct path in this case for me is this. Okay. And how does this prop file look like? Similar to in the thermal case, they are defined in exactly the same way, and we have to define 5 different properties. We have to define the yield stress as a function of the phases and temperature, the shear modulus, the bulk modulus, the density, and these are the trip parameters. So I've disabled trip effects here right now, so this is all set to 0. What's different from the thermal input file is that in thermal input file we specified basically for 2 phases. So we had the ferrite, pearlite, bainite, and martensite phase. We had 1 property because for thermal properties, these are all BCC phases, so they don't change that much. And we had a different property for the austenite. Here we have individual properties for all the phases. So here again, 2 temperature data points for 10 and 1500 degrees Celsius. And then this is a property for ferrite, pearlite, bainite, martensite, and austenite. You can see, for example, the yield stress of martensite is much higher here than the yield stress for austenite. So this is again a simple input file with 2 data points per temperature. I have annotated data from JMAT Pro over here, where we have 50 input points per data. So we can use this file in our simulation. Yeah, this one. Should now be able to run the simulation. Let's open our command prompt again. And the job name, and let's say mechanical. The input file that we want to use is the one with the inserted state-dependent variables. Want to specify a user subroutine. It should be, in this case, sim mechanical.f90, and I'm going to specify interactive to make sure it keeps running in the foreground. Our Abacus job is now completed, so we can go to Abacus, open the mechanical output database file, it's on here, and plot, for example, the stress from isostress. As you can see here, Abacus actually exaggerates the deformations. You can change that by going to common options here. And with this deformation scale factor, well, either to 1 gives already a pretty good idea. But let's just put it to 0. So no the deformation is not shown on the mesh itself. And now you can see the residual stresses, or the stresses in the x direction, or the amount of plastic deformation